On the first day, I talked about uncertainty arising principally out of three important sources, namely our ignorance, the complexity of the phenomenon, as also the model which we use to represent that system, and also ambiguity. These were three important sources which led to uncertainty. Uncertainty about the results we obtained, about our conclusions, and so on. And we have developed over the years certain methods or even techniques as well as supporting softwares to deal with such uncertainties. When I say to deal with, essentially our idea was to remove uncertainty, but uncertainty cannot be completely removed. It can be possibly reduced. And to reduce uncertainty in the procedures we follow, in the results we obtain, in the conclusions we reach, one attempt could be that we try to learn from other sources. That whatever we have already learned, maybe in a slightly different phenomenon, in a slightly different context, can be taken advantage of. So that, again, the original objective of reduction of uncertainty can be achieved. Statistical transfer learning has been studied over the last roughly 8-9 years. The first article appeared in 2010. And that way, I myself studied the topic roughly 3-4 years back. And I thought that it would be a good idea to exchange the notion behind statistical transfer learning with young research workers. Most of you are familiar with machine learning, I believe. Traditionally, machine learning helps you to carry out one particular task. By a task, I mean something like fitting a regression, or clustering of different individuals into clusters or groups, or maybe discrimination between two groups or among several groups, or maybe prediction. These are tasks for research workers, right? Research workers in all branches of science, they face certain common tasks. The tasks are, as I said, clustering, classification, discrimination, prediction. These are certain tasks. And whenever a task, by following a certain established procedure, becomes computationally quite involved, we take recourse sometimes to machine learning algorithms. So we have one given task, and this is to be carried out in a given domain. The domain would imply a particular data set. This data set could be quite large, could be having several variables pertaining to a large number of individuals, could be amenable to being partitioned into several subsets, but there is one data set. And a domain could relate to a particular group of individuals, a particular location, a particular point of time or a certain interval of time. So that way we have got a task to be carried out in a domain, and in the domain we have got a data set for which we assume what may be called broadly a joint distribution. So given a data set with a given joint distribution, we have to carry out a certain task in a certain domain. The given domain in which the task has to be carried out is called the target domain. The task to be performed is called the target task, and there is a target data set with an assumed joint distribution. So you have a target task to be carried out in a target domain and over a target data set. And this task, in terms of the computational complexity, is facilitated if we take recourse to machine learning algorithms. Let me illustrate with one which I believe most of you should be knowing, is the use of support vector machines. SVM. Can I assume that most of you are aware of support vector machines?
I don't know. I have only heard the name, nothing more than that.
Okay. I will briefly tell you. This is just a glimpse I said, and that's a part of it. A support vector machine is used again for the purpose of classification and discrimination. We have got a data set, a single datum pertaining to one individual could be a set of several variables, a vector, and it's pretty well known that in the group we can definitely identify at least two different clusters or two different classes. Initially, I don't know which individuals belong to class 1, which individuals belong to class 2. So it's something like a two-class discrimination problem. You have the famous Fisher's discriminant rule, you have the Bayesian procedure to calculate costs of misclassification, etc., to carry out the task of classification. Here what you do is, we try to fit in the data plane, I mean a multidimensional plane, what may be called a hyperplane. A hyperplane could be a straight line in a two-dimensional situation. Otherwise, in a high dimensional space, it's also, I mean, something like a hyperplane, we call it. The hyperplane is so determined that points which belong to the first class, points are corresponding to individuals which belong to the first class, are as far removed from the hyperplane, say to the right. Individuals belonging to the other class, the points representing them, they are as far removed from the hyperplane to the left. So there is a maximum separation between the two clusters of points, one lying entirely to the right of the hyperplane, the other to the left of the hyperplane. So that way it's a classifier rule, a linear classifier rule. There could be complicated nonlinear classifier rules also based on cardinal functions. That I am not going into, but basically a support vector machine tries to look at the pattern of the individuals and their corresponding vector values of the variables involved, to try to identify a hyperplane which will be as far possible from one group, say to the right of the hyperplane, and also as far as possible from individuals in the left part, I mean to the left of the hyperplane. So to find out the hyperplane in such a way that the separation is maximum is the task involved in support vector machines.
Why is the name so, support vector machine?
Why?
Why is the name so?
The name is derived from the fact that if you remember something of linear optimization or linear programming, we find out what is called a supporting hyperplane, right? The feasible space is supported, that way this is also called a support vector machine. It tries to find out a supporting hyperplane. We have got a separating hyperplane that separates the two, and a separating hyperplane that touches at least one point of the feasible space in the case of linear programming would have been called a supporting hyperplane. From that we derive the nomenclature support vector machine. I am not talking of support vector machines. There's a whole lot of literature on support vector machines, and basically a classifier rule. And this is something quite new. I was simply telling that statistical transfer learning is distinct from machine learning. Machine learning is useful for carrying out one particular task in one particular domain, right, with a particular data set. Whereas, and there will be a lot of uncertainty in the results that you ultimately derive. We are in the world of uncertainty right in this room at least. And to reduce uncertainty, what we can do is, we have other domains called source domains. There are data sets available called source data sets. This was target domain and target data sets. We can definitely derive knowledge. We can transfer knowledge already achieved in the source domains dealing with source data to reduce uncertainty about the conclusions we are going to reach in the target domain about the target task. The task remains more or less the same in the other source domains or source data sets. The source data sets definitely also follow a joint distribution which should not be in that case the advantage really fails. The same as the joint distribution of the data set in the target domain. I have got a target domain in the sense that I am dealing with a particular data set, which, as I said, could be very large, could be amenable to being partitioned into several subsets also, but that's one data set with a given joint distribution which I have assumed for it. There are other domains where are data sets available, they have their joint distributions, at least in terms of parameter values. The source domains have got joint distributions for their data sets which are different from the parameters of the joint distribution assumed from the target data set. Otherwise, we won't be able to take advantage of the learning obtained in the source domains. So the idea is that I am dealing with one particular data set called the target data set, dealing with a particular domain called the target domain, but I can transfer whatever knowledge has been already achieved by me or by others in the other source domains where I have got other data sets having joint distributions which are not totally unrelated from the joint distribution I assume for the target domain. In some way or the other, those joint distributions have to be related to this particular assumed joint distribution for the target domain or the target set. So that way, it can even take into account multiple tasks, at least multiple domains are being handled, multiple data sets are being handled. If I assume all those source data sets along with the target data set as only one bigger data set, then I lose the information that possibly from one data set to another, one domain to another, there are genuine differences which I will not be able to keep a track of. Therefore, I won't merge them. It's not a question of merging source data sets into the target data set, because in that case I will lose information about distinctiveness of the different source domains and the corresponding data sets characterized by joint distributions with different parameter values. I want to retain that. At the same time, those distributions being related in some way or the other with the distribution I assume for the target data set, I take advantage of that. So retaining the distinctiveness of the different source domains, how do I take advantage of this knowledge? I normally avoid looking at this, but then এইটা তো না পরেরটা